A propeller is a type of fan that transmits power by converting rotational motion into thrust. A pressure difference is produced between the forward and rear surfaces of the airfoil-shaped blade, and a fluid is accelerated behind the blade. Propeller dynamics, like those of aircraft wings, can be modeled by either or both Bernoulli's principle and Newton's third law. A marine propeller of this type is sometimes colloquially known as a screw propeller. A screw. However, there is a different class of propellers known as cycloidal propellers. They are characterized by the higher propulsive efficiency, averaging 0.72 compared to the screw propeller's average of 0.6, and the ability to throw thrust in any direction at any time. The disadvantage is a higher mechanical complexity and higher cost. History. Early developments. The principle employed in using a screw propeller is used in sculling. It is part of the skill of propelling a Venetian gondola, but was used in a less refined way in other parts of Europe and probably elsewhere. For example, propelling a canoe with a single paddle using a pitch stroke, or side-slipping a canoe with a scull, involves a similar technique. In China, sculling, called lu, was also used by the 3rd century AD. In sculling, a single blade is moved through an arc from side to side, taking care to keep presenting the blade to the water at the effective angle. The innovation introduced with the screw propeller was the extension of the arc through more than 360 degrees by attaching the blade to a rotating shaft. Propellers can have a single blade, but in practice there are nearly always more than one so as to balance the forces involved. The origin of the screw propeller starts with Archimedes, who used a screw to lift water for irrigation and bailing boats, so famously that it became known as Archimedes' screw. It was probably an application of spiral movement in space to a hollow segmented water wheel used for irrigation by Egyptians for centuries. Leonardo da Vinci adopted the principle to drive his theoretical helicopter sketches, of which involved a large canvas screw overhead. In 1784, J.P. Pawkin proposed a gyrocopter-like aircraft using similar screws for both lift and propulsion. At about the same time, James Watt proposed using screws to propel boats, although he did not use them for his steam engines. This was not his own invention, though Tugad and Hayes had patented it a century earlier, and it had become a common use as a means of propelling boats since that time. By 1827, Czech-Austrian inventor Joseph Ressel had invented a screw propeller which had multiple blades fastened around a conical base. He had tested his propeller in February 1826 on a small ship that was manually driven. He was successful in using his bronze screw propeller on an adapted steamboat. His ship, Civetta, with 48 gross registered tons, reached a speed of about 6 knots. This was the first ship successfully driven by an Archimedes screw-type propeller. After a new steam engine had an accident, his experiments were banned by the Austro-Hungarian police as dangerous. Joseph Ressel was at the time a forestry inspector for the Austrian Empire, but before this he received an Austro-Hungarian patent for his propeller. He died in 1857. This new method of propulsion was an improvement over the paddle wheel, as it was not so affected by either ship motions or changes in draft as the vessel burned coal. John Patch, a mariner in Yarmouth, Nova Scotia, developed a two-bladed, fan-shaped propeller in 1832 and publicly demonstrated it in 1833, propelling a rowboat across Yarmouth Harbour and a small coastal schooner at St. John, New Brunswick. But his patent application in the United States was rejected until 1849 because he was not an American citizen. His efficient design drew praise in American scientific circles, but by this time there were multiple competing versions of the marine propeller, screw propellers. Although there was much experimentation with screw propulsion until the 1830s, few of these inventions were pursued to the testing stage, and those that were proved unsatisfactory for one reason or another. In 1835, two inventors in Britain, John Ericsson and Francis Pettit Smith, began working separately on the problem. Smith was first to take out a screw propeller patent on the 31st of May, while Ericsson, a gifted Swedish engineer then working in Britain, filed his patent 6 weeks later. Smith quickly built a small model boat to test his invention, which was demonstrated first on a pond at his Hendon farm, and later at the Royal Adelaide Gallery of Practical Science in London, where it was seen by the Secretary of the Navy, Sir William Barrow. Having secured the patronage of a London banker named Wright, Smith then built a 30-foot, 6-horsepower canal boat of 6 tons berth and called the Francis Smith, which was fitted with a wooden propeller of his own design and demonstrated on the Paddington Canal from November 1836 to September 1837. By a fortuitous accident, the wooden propeller of 2 tons was damaged during a voyage in February 1837, and to Smith's surprise the broken propeller, which now consisted of only a single turn, doubled the boat's previous speed, from about 4 miles an hour to 8. Smith would subsequently file a revised patent in keeping with this accidental discovery. In the meantime, Ericsson built a 45-foot screw-propelled steamboat, Francis B. Ogden, in 1837, and demonstrated his boat on the River Thames to senior members of the British Admiralty, including Surveyor of the Navy Sir William Simmons. In spite of the boat achieving a speed of 10 miles an hour, comparable with that of existing paddle steamers, Simmons and his entourage were unimpressed. The Admiralty maintained the view that screw propulsion would be ineffective in ocean-going service, while Simmons himself believed that screw-propelled ships could not be steered efficiently. Following this rejection, Ericsson built a second, larger screw-propelled boat, the Robert F. Stockton, and had her sailed in 1839 to the United States, where he was soon to gain fame as the designer of the U.S. Navy's first screw-propelled warship, Princeton. Apparently aware of the Navy's view that screw propellers would prove unsuitable for seagoing service, Smith determined to prove this assumption wrong. In September 1837, he took his small vessel to sea, steaming from Blackwall, London to Hythe, Kent, with stops at Ramsgate, Dover and Folkestone. On the way back to London on the 25th, Smith's craft was observed making headway in stormy seas by officers of the Royal Navy. The Admiralty's interest in the technology was revived, and Smith was encouraged to build a full-size ship to more conclusively demonstrate the technology's effectiveness. SS Archimedes was built in 1838 by Henry Wimshurst of London, as the world's first steamship to be driven by a screw propeller. Archimedes had considerable influence on ship development, encouraging the adoption of screw propulsion by the Royal Navy. In addition to her influence on commercial vessels, trials with Smith's SS Archimedes led to the famous tug-of-war competition in 1845 between the screw-driven HMS Rattler and the paddle steamer HMS Electo, the former pulling the latter backward at 2.5 knots. She also had a direct influence on the design of another innovative vessel, Isambard Kingdom Brunel's SS Great Britain, then the world's largest ship and the first screw-propelled steamship to cross the Atlantic Ocean in 1845. propeller design stabilized in the 1880s. Aircraft propellers. The twisted aerofoil shape of modern aircraft propellers was pioneered by the Wright brothers, while some earlier engineers had attempted to model air propellers on marine propellers. The Wrights realized that a propeller is essentially the same as a wing, and were able to use data from their earlier wind tunnel experiments on wings. They also introduced a twist along the length of the blades. This was necessary to ensure the angle of attack of the blades was kept relatively constant along the length. Their original propeller blades were only about 5% less efficient than the modern equivalent. Some 100 years later, the understanding of low-speed propeller aerodynamics was fairly complete by the 1920s, but later requirements to handle more power in smaller diameter have made the problem more complex. Alberto Santos Dumont, another early pioneer, applied the knowledge he gained from experiences with airships to make a propeller with a steel shaft and aluminium blades for his 14 bis biplane. Some of his designs used a bent aluminium sheet for blades, thus creating an airfoil shape. They were heavily undercambered, and this plus the absence of lengthwise twist made them less efficient than the Wright propellers. Even so, this was perhaps the first use of aluminium in the construction of an airscrew. Types of marine propellers. Controllable pitch propeller. One type of marine propeller is the controllable pitch propeller. This propeller has several advantages with ships. These advantages include the least drag depending on the speed used, the ability to move the sea vessel backwards, and the ability to use the vane stance, which gives the least water resistance when not using the propeller. Skewback propeller. An advanced type of propeller used on German Type 212 submarines is called a skewback propeller. As in the scimitar blades used on some aircraft, the blade tips of a skewback propeller are swept back against the direction of rotation. In addition, the blades are tilted rearward along the longitudinal axis, giving the propeller an overall cup-shaped appearance. This design preserves thrust efficiency while reducing cavitation, and thus makes for a quiet, stealthy design. A small number of ships use propellers with winglets similar to those on some airplanes, reducing tip vortices and improving efficiency. Modular propeller. A modular propeller provides more control over the boat's performance. There is no need to change an entire prop when there is an opportunity to only change the pitch of the damaged blades. Being able to adjust pitch will allow for boaters to have better performance while in different altitudes, water sports, and/or cruising. Protection of small engines. For smaller engines, such as outboards, where the propeller is exposed to the risk of collision with heavy objects, the propeller often includes a device that is designed to fail when overloaded. The device of the whole propeller is sacrificed so that the more expensive transmission and engine are not damaged. Typically in smaller and older engines, a narrow shear pin through the drive shaft and propeller hub transmits the power of the engine at normal loads. The pin is designed to shear when the propeller is put under a load that could damage the engine. After the pin is sheared, the engine is unable to provide propulsive power to the boat until a new shear pin is fitted. In larger and more modern engines, a rubber bushing transmits the torque of the drive shaft to the propeller's hub. Under damaging load, the friction of the bushing in the hub is overcome and the rotating propeller slips on the shaft, preventing overloading of the engine's components. After such an event, the rubber bushing may be damaged. If so, it may continue to transmit reduced power at low revolutions, but may provide no power, due to reduced friction at high revolutions. Also, the rubber bushing may perish over time, leading to its failure under loads below its designed failure load. Whether a rubber bushing can be replaced or repaired depends upon the propeller. Some cannot, some can, but need special equipment to insert the oversized bushing for an interference fit. Others can be replaced easily. The special equipment usually consists of a funnel, a press and rubber lubricant. If one does not have access to a lathe, an improvised funnel can be made from steel tube and car body filler. As the filler is only subject to compressive forces, it is able to do a good job. Often, the bushing can be drawn into place with nothing more complex than a couple of nuts, washers and a threaded rod. A more serious problem with this type of propeller is air frozen on spline bushing, which makes propeller removal impossible. In such cases, the propeller must be heated in order to deliberately destroy the rubber insert. Once the propeller is removed, the spline tube can be cut away with a grinder and a new spline bushing is then required. To prevent a recurrence of the problem, the splines can be coated with anti-seize, anti-corrosion compound. In some modern propellers, a hard polymer insert called a drive sleeve replaces the rubber bushing. The spline or other non-circular cross-section of the sleeve inserted between the shaft and propeller hub transmits the engine torque to the propeller. Rather than friction, the polymer is weaker than the components of the propeller and engine, so it fails before they do when the propeller is overloaded. This fails completely under excessive load, but can easily be replaced.